Now that we have properties of dot product and we have the dot product and we're a bit comfortable with it, I want to use this dot product to prove nice geometric results. So here's one example. Um, a rhombus is a parallelogram whose sides have equal length. So a diamond, a rhombus, a losange, all of these things just means the sides all have equal length. So here, this vector v and this vector w have the same length. All right, so I want to prove something about a rhombus. I want to show that the diagonals of a rhombus intersect perpendicularly. Right, so let's draw our rhombus. I have V here, the other side will be V as well. Now let me use a different color, let me use blue. And then I have W here, and I have W here. All right, so what we're given, since it's a rhombus, we're given that the length of V is the same as the length of W. Then we're asked about the diagonal of a rhombus. Well, we've seen how to get to the diagonal before. We have this diagonal, let's call it D1, and we have this diagonal, let's call it D2. Of course, it doesn't matter which way you draw the arrows. As long as you're consistent, you'll be you won't be penalized if it's different from mine. So here what we want is we want to prove that these diagonal intersect perpendicularly. So goal, I want D1 perpendicular to D2. Let's translate that right away using dot products. So D1 perpendicular to D2, that means that the dot product of D1 and D2, I want to show that this is 0. I like writing this right away because it gives you something to work towards. It gives you something to start with. It gives you d1 dot d2. I need to compute this. So right now I like this. I'm going to work on d1 dot d2. All right, d1 dot d2, that's what I want. I'm going to work to get an expression of d1 and d2 using the vectors v and w because all the information I'm given is in terms of v and w. So d1, that's the red one. We've already done this, but let's do it again. So I want to start here and end here. I could go either way. Let's go up. So I do V first, same direction as the arrow. So that's plus V. And then I follow W. Again, same direction as the arrow. So V plus W. Now D2 is the orange one. So if I start at this point and end at this point, I'm going to go the opposite direction as the arrows for V. So that's minus V, and then the same direction as the arrows here. So this one is minus V plus W. So I'm ready. I want to compute d1 dot d2, and I want to show that it's 0. So d1 dot d2, I'll replace it with v plus w dot minus v plus w. And now we expand. So I'll expand this way. I'm going to get minus v dot v. I'm going to get plus v dot w. And then I'll get these two, which will give me, actually I don't want to be squished on the side. Let's put it here. I'll get minus w dot v. I'll get w dot w. And so now since the dot product is commutative, these cancel. And so all I get is minus the length of v plus the length of w squared. But these are equal. Length of v is equal to length of w, so this will give me 0 as the length of v is equal to the length of w. This is the only place where I'm using the fact that I have a rhombus. Everything I've done before works for any parallelogram. But now, because I have a rhombus, I have this extra fact, and I can make this jump right here. All right, so d1 dot d2 gives me 0, and so the diagonals d1 and d2 are perpendicular. All right, so here's the whole problem. These are quite nice. I'm using the properties of dot product, and I'm using the definition of a rhombus, and I get that d1 dot d2 equals 0, and that's the same thing as saying that d1 is perpendicular to d2.